сверх какого-то числа. Hello.
Hello everyone, good morning. There are only 3 of us
Hello.
currently. Hello, yes. We are starting shortly when more students join in. Let's wait a bit. Hello once again. Today we are going to finish our discussion of the Ethereum architecture, Ethereum virtual machine, and how smart contracts are executed in the Ethereum environment. And there will be just two concluding lectures next week, in which we will discuss the Hyperledger, the modern Hyperledger architecture. We have already touched upon the fourth generation of distributed ledger systems, which is our own in the chain, currently under development at our Innopolis University. By popular request, I think there was a request that we do our final exam not on the 20th of December, but as soon as possible after completion of the course. We'll try to do it. Actually, I made a request with the Department of Education and awaiting the response. Uh, so not obviously the next week yet, but I think the following week we'll have our exam. Can you tell me, please? So your examination session, when does it start officially?
At 6th of November. I mean December.
December. So at the 6th of December.
The first one,
Okay,
I guess.
so which day is it? Is it Monday already?
It's I guess it's from Monday next week.
Oh, it's from Monday next week. So in that case, what does it mean? That it would be extremely inconvenient for you to have a lecture on Monday, or how?
Actually, it's okay because we don't have any like inter
You don't have any
lectures occurring at the same time.
Okay.
If you will be in like if you
Yes.
want to move the lecture in any other slot.
So Monday standard time would be okay for you.
I guess yes.
Okay, that's wonderful. And I think
Let's just communicate it through the representative,
we
so
will, yeah.
she may address this issue directly.
Okay, but I could even do a double lecture because we need to consider one or two, we'll see, Hyperledger in detail, and then we're done. So we're done with all our objectives. Fine. So in this course, we obviously touched upon Solidity smart contract programming, and there is another language for smart contract programming, actually several, in Ethereum. Another popular, not as popular as Solidity, but gaining popularity one is called Viper, which emphasizes better security than in the original Solidity framework. But I specifically do not dwell that much on them because the next term we will have a full-fledged smart contract and distributed application programming course. And in that one, we'll be able to discuss all aspects related to real programming of distributed ledger systems using different technologies in much detail. Our objective this time was to familiarize ourselves with the basic concepts, principles, and so on. So we know in particular quite well about the key concepts like consensus, in particular smart contract virtual machines, distributed state, proof of work. We're going to discuss proof of stake, and so on. Okay, So several important things we are going to discuss today. So let us probably begin with the notion of consensus in Ethereum. There are two principal ways of how consensus can be implemented. As we already know, well, there are several proof of X ways of how the system can be secured. In particular, in Ethereum, it is the classical proof of work and proof of stake. Proof of work is the current one. Proof of work was intended to be replaced by proof of stake, but not replaced yet. In proof of work, the algorithm for Ethereum is called Ethereum hash, which is approximately same as for Bitcoin, but not exactly same. So let us recall how is proof of work implemented in Bitcoin. The system challenges you by providing you with the difficulty level. So there is a certain difficulty level, which is computed centrally by the whole network. So as part of the consensus protocol, block by block, when new blocks are introduced into the system, then difficulty is automatically adjusted at the block number. Well, first of all, at the block number, and also, if you remember, at the amount of time required to hash previous blocks, a certain number of previous blocks, or a previous speed, which may increase or decrease. But on average, we have about one block in 10 minutes in Bitcoin. Roughly same, which you remember, any miner in Bitcoin was on average succeeding with the average capacity available to him, was able to succeed in hashing a new block once in 70 days, roughly. In Ethereum, it is roughly same in the sense that the typical complexity would be about 2, as far as I remember, terahash operations, and 1 terahash would require typically 50 days. So we would say roughly 1 block in 100 days. That's what an Ethereum miner would typically be able to do. So roughly on the same scale. But although the objective is to compute a hash of something with the value less than the difficulty, and obviously increasing the difficulty, making it more difficult, means actually lowering and lowering the threshold, actually. But of what this hash is computed is quite different between Bitcoin and Ethereum. So in Bitcoin, you remember, there is a transaction. There are a few variable fields in this transaction, such as timestamp, which you can alter with some limits. You can't make it 1 hour in the past or in the future, but you can tweak, for example, uh, any fractions of seconds and maybe seconds. And there is a special field which is called nonce and its extension in the modern day standard. So you tweak them, and by tweaking them, you are hashing the whole block, and you are trying to get the hash value less than the difficulty threshold specified. So basically, your variables are just a few fields which you could alter within the block. In Ethereum, in ETHash, there is an interesting algorithm based on directed acyclic graphs or DEGs. Obviously, you remember graph theory from even the first year. You know what these directed acyclic graphs are. These are directed graphs in which edges or arcs have directions, but without any cycles. So navigating such a graph would always terminate. You wouldn't be able to encounter any infinite loop in it. And what happens is that the system, as part of the node functionality, generates those large graphs for you, which are really large. When stored, how can we store a graph? A graph is stored as a matrix of node connectivities. I mean nodes of the graph and not nodes of the Ethereum system. So you can think of it as a square matrix, and this square matrix would provide, for example, between some I and j, it would provide +1 if there is an arc from I and j, node I to node j. Obviously, 0 if there is no connection between them. And then if we transpose it, so map it across the main diagonal, then another one from j to I would obviously be -1. That's how we store in general information about directed graphs. And imagine that the graph is big, so you need about the whole gigabyte of memory in order to store such a graph. The graph is automatically generated by the nodes as part of the node operation algorithm in, I would say, deterministic way. In such a way that it is gradually being replaced and replaced and replaced by new values, and roughly every 3000 blocks, the graph becomes completely new one. In that case, what you need to do in order to hash the current transaction, not just you would alter some fields within the current block in order to get the hash. But what you really need to do is to pick up some small isolated subgraphs of the current graph, picking them at random, include the representation, let's say matrix representation of those subgraphs into the value you need to hash, and hash it along with the block. So your space of variables is much larger in this case. In Bitcoin, there are only a few variables which you could tweak in the block and then hash it. Whereas Ethereum, in the form of the Ethereum runtime system and Ethereum node, provides you with a very large set of values which you could alter. I mean, not alter because it is a fixed one, but you could pick up values from it, append them to your current block, and try to compute a hash. Obviously, there is absolutely no way to predict which values of this graph you need to pick up in order to get the hash below the threshold. So you try and try and try, extracting them from the graph, and eventually, hopefully, you succeed once in 100 days. And as a miner, it is the same mining process, you manage to hash the whole block. Why is it important? In Bitcoin, the original 32-bit nonce had become a very significant limitation from the very beginning. You remember, just within the few years when the number of blocks was not that high yet, it was okay, and the difficulty was at that time still quite I would say easy, where then the nonce itself, a 32-bit one, became insufficient. You had to tweak the timestamp and then find other ways of what you could alter within the block in order to get sufficient randomness uh, to change, to alter in the search for the value which would bring your hash below the threshold. In Ethereum, you are immediately by construction of the blockchain node, you are given a huge space to search in, which avoids all these current and future technical problems with uh, hashing the blocks. And also, you can note that, for example, hashing an Ethereum block is just computationally intensive, whereas hashing the Bitcoin block, hashing the Ethereum block is not only computationally intensive, but it is to some extent memory intensive because you need to navigate this large data structure. This was deliberate. This was deliberate in the sense that what do people do, for example, in order to improve efficiency of mining in Bitcoin? They started from conventional CPUs. What do people do then? What they started doing? Using GPUs. GPUs are graphical processing units, typically from NVIDIA, which allow you not only to render your graphics, but they can be used as very powerful parallel processors for computations, for general purpose computations. Excuse me, please, 1 second. I will get back to you in a second. Okay, are you familiar with GPU computing, by the way? Have you been doing anything to compute on GPUs
Yes.
on NVIDIA? Yes? What have you been doing with them?
We have done some data learning, or machine learning, and to train our models using CUDA course.
Oh, okay, okay. Was it what Python TensorFlow GPU enabled, or you implemented your own GPU program? So did you program directly in CUDA?
No, just use
Oh,
some PyTorch and other
okay.
similar
Ah, it was
programs.
Torch. It was Torch, not TensorFlow, but Torch. Great. Okay, yes. So currently, many machine learning backends are indeed GPU enabled. You can do actually quite a lot with GPU programming. So there are several ways actually of how you can program them. This might be interesting actually. So what you can do? There is a framework which is called OpenCL, which can be used to that end. And it is not only for NVIDIA GPUs, but for other GPUs and indeed symmetric multiprocessor common cores, classical cores as well. There is obviously the CUDA API. There is currently yet another API which is called Vulkan. Uh, all of them, especially Vulkan, are quite low level. CUDA is reasonably high level for C++, so it is a relatively easy to use C++ environment. But even then, you need to take into account many things like, for example, optimal memory allocation, things like that in GPU. And this is okay, but still becoming tedious to some extent, especially what is I wouldn't say difficult, but still tedious in your programming is CPU GPU communication. There are several ways of how you can load your data into GPU and get the results back from GPU. So then new standards for parallel computing emerged, especially for C++ and Fortran. You have probably heard about them. One of them is called OpenMP, and another one is OpenEC. OpenMP is for high-level parallelization on both actually CPUs. The initial emphasis was for CPUs, but then it became available for GPUs as well. OpenEC was for GPU offloading only. So for example, even the GCC compiler, it supports both actually OpenMP and OpenEC, although when I was trying to run it in OpenEC mode with CUDA, it achieved almost no speed up. So basically, its support is quite poor in GCC. But there is another compiler from NVIDIA itself. Currently, it is owned by NVIDIA, which is called PGI. PGI C++. PGI is the original owner of the compiler, the company called Portland Group Incorporated, which was eventually acquired by NVIDIA, but the name of the compiler still stands. And PGI supports OpenMP and OpenEC very well, achieving very easily through C++ pragma constructs, achieving very easily a high degree of parallelization, similar to that which you can achieve by manual CUDA programming. So at the moment, this is probably the preferred way of how you can do GPU programming. From other languages like Python, we would typically do Python by itself, obviously, cannot run on a GPU. Python interpreter is not running on a GPU. GPU is for floating point computations only, for well, integer and floating point, but it has very poor things like dynamic memory management, even flow of control is detrimental to the GPU. It is much better if you execute a single code, multiple data paradigm. So basically you have multiple GPUs, but the control flow through all of these GPUs is exactly the same. So if, for example, one GPU forked and executed, for example, the first branch, and another one executed the second branch, then this would already be highly detrimental to the GPU performance in general. So it's not for general purpose computing, really. It is for very much symmetric single instruction multiple data computing, and that's why Python interpreter runs on the CPU, and then computational nodes or kernels, as it is called, which can be offloaded to the GPU, are really offloaded to the GPU, which can be executed very efficiently with high degree of parallelism, but really symmetric instruction execution. That's how implementations of Torch or TensorFlow make use of GPU. But why stop here? Okay, we're trying to speed up our hashing. We are miners and we're investing money into more and more speed. Okay, from CPU, multi-core CPUs, to GPUs, and there are huge farms with maybe thousands of graphical cards, graphics cards executing this GPU code, which is in particular good if you have free electricity, and then you can do mining, and free electricity can be obtained by tapping, illegally tapping into electricity supply. This happens very often, actually. What else? Can we speed up our computations even further? CPUs, GPUs, what are other architectural things we can do in order to speed up our computations? What do you think?
We can design a chip which will be implementing the algorithm on the circuit itself. It's called ASIC, I think.
Yes. So basically, you can do exactly that. So you can achieve this with the help of a specific circuits. There are several ways of how this can be done. Um, so specific integral circuits. Sometimes you can use technologies like, for example, FPGA, field programmable gateway arrays. To that end, for example, Altera or Xilinx. Have you seen actually FPGA in action? Maybe you have some experience with them.
Yeah, we had a few labs on them during our freshman year.
Oh, okay, great. What do you think? What are the strong and weak features of, I wouldn't say about any just, specifically designed integrated circuits. Obviously, if you order a specific circuit to support this type of computation, you can really make it very efficient by tailoring it to precisely the hashing functions you want to compute, but that's expensive. That's really expensive because you need to order a design. Design is very expensive, and the generic design, I mean, not FPGA, because FPGA is specifically developed for just reconnecting this gateway arrays and then getting your circuit design done. But if it is just a custom ordered integrated circuit, then of course it is much more expensive than FPGAs. Let's think about FPGAs for a moment. What do you think are the strong and weak features of FPGA if used for mining?
They're quite expensive to scale, actually, because the one unit is not that cheap if we will not consider the design cost, I mean the production cost. And they are not that simple to program actually, and you can end up with the sequential logic, which is not what will benefit you mostly, because we need to parallelize everything, and the sizes of gates are quite small, and not every algorithm can fit there. So we need to speed up only some parts, let's say matrix multiplication or something like this. I mean, only small parts of the algorithm, not the entire.
Generally, yes. So I think you're absolutely right about them. So very well, I think, structured. First of all, one interesting thing is that they have a relatively low clock speed compared to conventional CPUs. So for example, typical clock speed of an FPGA is about 1 gigahertz, not 4 or 5. That's number one. Number two, yes, design is difficult. Not as difficult as it would be for a completely new custom specific integrated circuit, but or application specific integrated circuit, but still difficult. In order to design your FPGA application, you can use either OpenCL, same OpenCL as could be used in GPU computing. But then you're absolutely right that, for example, using OpenCL doesn't allow you to gain most advantages of the speed from your FPGA, which underuses your potential, possibly restricts the degree of parallelization. And in fact, my experience, I was attempting to use FPGAs not for mining, but for algorithmic trading in place of standard CPUs. And the conclusion was that, in particular, doing it in OpenCL would, in most cases, produce a design inferior worse than the conventional CPUs. So OpenCL is generally a bad idea. Using specific hardware design languages, like for example Verilog and family, is better, but in this case you need to be really a specialist in hardware design. So Verilog, OpenVL, and languages like that are for, I would say, qualified hardware designers. And another interesting thing is that FPGA solutions are typically nearly memoryless. So for example, you can implement a logic which performs reasonably fast, let's say in parallel, if you are good in Verilog, fast and parallel direct computations through those field programmable gate arrays. But it is much more difficult to implement a logic which memorizes the values. So either you need to implement your memory directly using FPGA chip itself, or you would use an external memory directly connected to FPGA and use memory there, but then it would become, accessing this memory could become a non-parallel bottleneck, and you lose your speed also. So for computations, they can be very efficient. For, I would say, memoryless computations, or low memory computations. For computations which require memorization, they are much, much, much less efficient and yes, expensive. For example, a typical, let's say, Altera or Xilinx board would cost roughly 50K USD, whereas a GPU would cost roughly, I would say, 1.5K. And although you could do FPGAs for Bitcoin hashing, but one of the design objectives of Vitalik Buterin when it was his invention actually, when he proposed this DEG-based consensus in December 2013, it was that use of FPGAs and ACICs is discouraged. So this graph-based computation is extremely difficult to achieve on application-specific ICs and FPGAs. Why? Precisely because it is memory intensive. So you really need to, first of all, crawl over a large, probably gigabyte size memory, selecting various pieces of your graph, attaching them to the block, and hashing. So specifically, the consensus algorithm for Ethereum is designed in such a way as people would not use custom designed hardware. They would offer almost no advantages. Whereas CPUs and, by the way, GPUs are okay. Application-specific ICs and FPGAs, not okay. Why do you think this design decision was put into Ethereum?
Maybe so it will be used by ordinary people, not the ones with the big wallet, and
Yes.
there will be no.
The whole region, you are absolutely right, is democracy. In Bitcoin, there is a possibility which is considered to be a real threat. It didn't materialize yet. At least there are no known examples of how this had really happened. Of a so-called 51% attack on the Bitcoin network. So if, for example, you assemble a vast computing farm, which accounts for example, 51% of the total computational capabilities available, then with a very high probability, sufficiently high probability, you and only you start hashing the blocks, which means that you can do whatever you want. So for example, you can eliminate transactions which you don't want from the system. You can reverse the history even to such to some extent. You can do absolutely any transactions which would be beneficial for you and not to other participants. So basically you seize control over the whole network in that case. And this is a real possibility. Well, I mean, an existing threat. And in order to prevent building up huge computational capabilities in the hands of a very few miners, then this specialist hardware is discouraged in Ethereum, whereas ordinary people using ordinary CPUs, GPUs, and free energy stolen from overhead transmission lines are very much encouraged to run Ethereum mining. I'm joking, of course, about the overhead transmission lines, you understand. Now, that's about the proof of work. But from the original intent, already at the time when Ethereum was introduced, it was decided that proof of work is to be gradually replaced by the proof of stake, as we have discussed. So basically, what is proof of stake? As we said, if you have significant interest or stake or made significant contributions into the Ethereum network, then you are allowed, proportional to your contribution, interest, merit, and so on, reputation, any other kind of stake, to hash new blocks. And you risk your assets, reputation, merit, anything else which is at stake if you do not follow the protocol. So if your node acts maliciously on the network, so for example, you are without any reasonable purpose trying to overrun existing transactions or hash invalid transactions and so on, then you would be hopefully overpowered by other nodes of the network, and moreover, you lose your stake, for example, reputation, other interest, whatever, and that's probably something which you don't want to lose, and that's why the majority of participants would choose to play by rules in the proof of stake system. So what could be your stake in the Ethereum network if we really implement a proof of stake? So what is your stake? Your good name in the academic community? Probably not. What could be at stake? What can you deposit
The
or risk? What?
maybe stake is amount of effort you put into computation, not in the computation, but the amount of data you store uh, in your node.
Of course, you are right. Well, almost correct. So your stake is really your Ethereum and nothing else. You do not store anything on your node. So the proof of stake protocol, actually there are two versions of it. The original one was called FFG, it's an abbreviation which stands for something obscure. And the more recent one is called CBC. FFG was a hybrid, proof of work, proof of stake. Discontinued by Buterin in mid 2018. It was easier to implement than the pure proof of stake CBC, which is a pure proof of stake. But the decision was made to evolve into pure CBC, pure proof of stake. Unfortunately, this CBC is still under implementation and not working. But the idea is the following. You really deposit to where? To some, again, general functionality of the whole network. So the nodes would be modified in such a way, all of them, that they allow deposits to be made by network participants in Ethereum, and proportional to the deposits made, allow them to hash the incoming blocks. So the difference between proof of work and proof of stake is actually not so big. If you do proof of work, then there are also assets at stake which you may lose, and you do lose, not only in case of your dishonest behavior. Obviously, if your behavior is completely dishonest, but you don't have this 51% of power, then you would not almost certainly, but completely certainly overrun by other network nodes, and you simply waste your computational time and electricity. So you're, first of all, waste electricity, and then, interestingly enough, hardware does also have amortization or wear out as a result of, for example, repeated electrical and heat fields applied to your hardware, it is deteriorating, and eventually your NVIDIA GPUs would start failing in your computational farm. So your hardware and your electricity are at stake. You lose them on average when 69 days out of 70 you do not succeed in hashing a block, but then you hash a block successfully, and hopefully you make up for your losses in the previous 69 days. Whereas in proof of stake, you lose your stake in Ethereum not only if you behave dishonestly. In that case, almost certainly you would lose your Ethereum because you are overpowered by other network participants. But simply if you are trying to hash a block, you put Ethereum at stake, and you didn't succeed, someone else came up first with a hash below the threshold and succeeded in hashing the block, then you still lose your stake. So from economic point of view, it becomes very clear. So we discussed already that proof of work is, in economic terms, is equivalent to gold money, right? Whereas proof of stake is, in this case, equivalent to paper money. The cost of producing your money itself is cheap. But in order to use paper money, when paper money could be used? When it is accepted by the majority of economic participants. So paper money originated in medieval China, right? Now, my question to you, when did paper money appear for the first time in Europe? Approximately. What's your idea? Not so long time ago, 300 years ago. Around 1720. A Scottish adventurist by the name of John Law arrived in Paris and proposed to the king. Actually, the king, Louis XV, was in his infancy at that time, so there was a regency council running the country in his place. So he proposed this idea to the council that in order to improve monetary circulation, he would set up a bank which prints or issues or emits paper money instead of gold and silver money as conventional at that time. And he was appointed by the finance minister. The system was in existence for about a year and then ran into hyperinflation and collapsed. John Law barely escaped Paris. But from overall economic point of view, as we discussed, paper money is much more advantageous than gold money, because a universal use of gold money would mean that 50% of the total effort, or the total working effort, is spent on extraction of gold, and the other 50% on producing goods and services which are valued in that gold. Whereas in paper money, although there is a risk of inflation, but there is no risk of wasting that much of public economic effort. So it is definitely the future of blockchain systems to move into the proof of stake. In that case, we'll stop burning the electricity, and put our ethers at stake or any other cryptocurrency in order to do hashing. But the challenges are exactly same, and there are challenges uh, in introducing paper money 300 years ago. You really need a wide public acceptance of this kind of value standard, which was not actually achieved in Europe until, I would say, the second half of the 18th century. Only after 1750. In Russia, it was during the time of Catherine the Great in 1867 when paper money started making progress into the economy. In a similar way, common blockchain systems are still dominated by proof of work, with the proof of stake being under development and hopefully will get acceptance soon. There are significant technical challenges as well.
That does it mean that potentially, if China has a half of assets and mining powers, it will be able to control everything because it has the hugest stake.
In proof of work, yes. There is certainly
In proof of stake, I mean, it has
in
a lot of
proof
assets.
of stake as well. Well, yes, maybe. But the question is, you see, proof of stake. Can we really say that, for example, the majority of ethers are owned by Chinese? Maybe. By the way, if you
Let's imagine this situation in some coins, not
yeah, yeah,
obligatory
yes,
Ethereum.
in that case, yes. But what we mean China would have the power in that case. It really depends. If these are private individuals and the majority of them appear to be Chinese, it still doesn't mean that they would take some kind of consolidated monopolistic action. But if, on top of that, the Chinese and the Communist Party of China decides to control those cryptocurrencies and orders the citizens, the Communist Party orders you to do a consolidated proof of stake action, which is not very likely, to be honest. But if it happened that way, then definitely yes. Then the operation of the whole network would be seized not by Chinese citizens actually, but by the Communist Party of China, acting as a monopolist through its political power and its political and legal influence over its citizens. In that case, yes. And
I
even
guess in case if it will appear, the price of the coin will go down drastically immediately.
it depends how they, maybe not immediately, how they manage to control it. It might be that they would start, first of all, just, trying to pump the price up, and then trying to sell the accumulated assets, keeping the price for a while, and then it crashes. It might be like that. To accumulate assets, drive the price up, then try to sell, but not so much aggressively in order to prevent others from recognizing the situation, and then eventually the price crashes like just a brick from clear sky. Yes.
And how much in percent, in average, the rotation of coins is circulating per day? Like how much of whole mass of the coins is moving
Um,
in some particular day?
it is a very good question actually, which I think we have seen some graphs for Bitcoin. You remember in terms of unspent transaction outputs, uh, because unspent, which mean that they are not touched. Uh, it's a really interesting point. Let's calculate. I don't remember the answer from the top of my head, but what actually prevents us from guessing? So there are 144 BTC transactions per day, right? Because
You
roughly
mean
once we can,
roughly
sorry, blocks,
this amount?
blocks,
Okay, blocks.
blocks, not transactions. Okay, one block is, as we know, roughly 250 transactions. Obviously, the monetary distribution of those transactions is very, very, very much uneven. But what would be a typical average transaction size? Okay. I would say if it is FX in classical fiat FX, then the average transaction size is $1 million. Here we would probably say, I would say in dollar amount, it is probably less than $100,000 because these transactions are still more or less democratic. Even accounting for very large transactions, which do happen, I think we can really say that it is less than USD 50K. Okay, 144 times 250 times, let's say 50K. Let's compute. What is it? Please compute.
It is $1.8 billion per day.
1.8 billion. Okay. Now total capitalization of, well, nowadays with cryptocurrencies reaching historic highs once again, we would say that, let's say the total capitalization would be around, well, roughly, I would say 500 billion, possibly more, of which about 60% belongs to Bitcoin. Therefore, I would say BTC, okay, total capitalization, okay, 300 billion. So it is 1 over 300, about 2 over 300, which is less than 1%. So I think it is realistic. So the daily turnover, in economic terms, it is called daily turnover of BTC, is about 1%. In terms of, for example, equities, a daily and equity trading, a daily turnover of 1% of capitalization is considered to be relatively low.
So that means usually if you want to, for example, control the whole market, then you will try to do some unexpected transactions. It will definitely be shown in the graph of amount of turnover
Yes,
per day.
yes. So because at least for those public blockchains, transactions are observed. You at each particular time you see the unspent transaction output and the state of so-called wallets. Although you may not know actually which unspent transaction outputs are associated with which wallets exactly, because there could be a person who controls, for example, thousands of private and public keys. So you don't know that they're under single control. But again, you can guess that by, for example, observing that historically those addresses moved sometimes in sync, which probably means that they are controlled by a single party. Or, for example, many transaction outputs destined to a particular set of public keys were serving as inputs to another huge transaction. So basically deriving associations between Bitcoin addresses or Ethereum accounts is possible. By the way, it is a very interesting task for machine learning. Using unsupervised learning and algorithms for cluster analysis, you can do something like that, and it is a very interesting task, I would say. Then you can imagine how it would work. So yes, we are waiting the arrival of proof of stake, but it is not quite there yet. And the second topic which I would like to discuss today is, as we wanted to do, the structure of the Ethereum virtual machine. For the complete instruction set, you can see the corresponding references. What I want is to provide some overview and highlight interesting things about this EVM. Are you familiar, for example, which virtual machine are you familiar in close detail? For example, Java virtual machine. Do you know how Java virtual machine works? What is the internal architecture?
Not really. We only studied the actual MIPS architecture, which is
Ah,
not
okay.
virtual but machine.
Yes, MIPS real architecture. Okay, Java virtual machine is somewhat different in the sense that it has a stack-based architecture and also a local set of registers. So it is not similar to any real hardware architecture and to some extent architecture neutral. So with Ethereum virtual machine, it is even more simple than that. So first of all, you can at least notionally think that a new instance of Ethereum virtual machine is created every time when a smart contract is to be executed. So basically, you remember there is a, let's say, human-driven EOA account with private keys, with a private key, which initiates a transaction. But the destination of this transaction is not another EOA. If it is another EOA, then there could be only one type of transaction between them, sending funds from one EOA to another EOA. All right? But the destination is a smart contract SC account. So basically, there is an account occupied by this smart contract, and then the transaction contains the address of this transaction is the address of the smart contract, and the data. Remember what the data are? The data are the arguments for the corresponding method to be invoked. So the first 4 bytes is the hash of the method signature, and the rest are the arguments, as we discussed last time. So what happens in this case? A new, or at least conceptually new EVM instance is created, a completely fresh one. It has a very, I would say, simplistic memory model. Actually, it has three types of memory. One of them is RAM, which is read-only memory. And this read-only memory contains, what do you think, what does it contain? It contains the bytecode of the smart contract. Bytecode to be run. Only that. Now, it has another kind of memory which is interesting. It is called storage. Storage is a persistent storage associated with this smart contract account. And that's very important. So although although the Ethereum virtual machine EVM invocation is transient, so it is created and then destroyed, at least notionally, but there is a storage associated with the whole smart contract account, and obviously physically this storage is in the blockchain. The corresponding data are then sent as part of the blocks and consolidated through the consensus across the whole blockchain. So you can implement memory in your smart contract invocations. So for example, one method would update your state, then another uh, transaction would invoke another method which makes use of this data and updates it further, and so on. So the existence of the storage is absolutely fundamental. And then as opposed to storage, there is what is called memory by itself, let's say transient, which is just a memory chunk initially zeroed out and the initial storage for your smart contract can be it can be initialized when the smart contract is deployed, and then you send data to the smart contract address. It initializes your storage. So this memory in the smart contract is actually organized as a stack. So let's say the top part is still zeros, and there is a stack growing upwards. There are no registers. There are load and store instructions of EVM, of the EVM. Typical load and store instructions, if you remember it from the MIPS architecture, they're about loading values from memory to registers and storing them from registers to back to memory. But EVM doesn't have registers. All operations occur between the top entries of the stack. So for example, if we perform addition, then two topmost items are at the top and replaced by the value. So load and store allows you to access other memory locations in the depths of your memory and put the corresponding values on top of the stack, advancing the stack pointer. And that's all. An extremely simplistic machine. What is important is that a smart contract, although we say that the original active entity is the EOA, so active, so a human-like account with the corresponding private key, and a smart contract is a passive one. It is activated, a method on a smart contract is activated when a transaction arrives with the address of the smart contract. But in fact, it is not entirely true. A smart contract can call another smart contract. Moreover, it can call another actually either another method belonging to the same smart contract account, or even do a cross-account call. And you remember that there is a cost associated with all transactions in Ethereum. It is a so-called gas. If you cascade calls to smart contracts, then if, for example, another smart contract is invoked through a remote call, then new instances of the virtual machine are created. So this was your original VM1, then VM2 is created, then VM3 is created, and so on. But obviously, they all run on the same supply of gas. I will explain the notion of gas in a little bit more detail very shortly, as was designed in the original smart contract invocation. So the original call, the original transaction was providing some amount of gas available. And subsequent calls run on the same gas until either they succeed or the whole gas is exhausted. So when gas is exhausted, you get a so-called out of gas exception, and it means that the transaction did not succeed. And that's why it is important that your virtual machines are transient. If a virtual machine, any of them, got an exception, then an exception propagates for out of gas, then the whole, either the virtual machine itself or even the whole chain of virtual machines created are completely destroyed. And therefore, the state of our Ethereum network is not at all affected in that case. So it is really transactional. Invocation of a smart contract is really transactional in the sense that either it runs to completion and then the state is modified, or uh, the state is restored to the original state before the transaction. You have any questions? No. Okay. Um, I already mentioned that gas is yet another cryptocurrency, or I would say unit of value, which is used in the Ethereum network in addition to Ethereum itself. However, gas exists only inside transactions for the purpose of running those transactions and executing smart contracts. In running the smart contracts, all operations have a fixed price in terms of gas, uh, as specified by the virtual machine specification. So this price doesn't change. And obviously it is related to the computational complexity of what you are doing. So for example, a simple addition when two items are at the top on the top of the stack are probably cheap, and therefore it is only 3 units of gas. However, if you compute a hash using this Kazakh 256 hashing function, you remember, then the cost is significantly higher. It has a fixed cost of 30 units of gas plus 6 units per each 256 bytes of data to be hashed. Hashing of data using this hashing function is implemented, we have seen it actually in the pseudo assembly code, as a single instruction within the Ethereum virtual machine. So that's already significant. But what is more significant is that just initiating any transaction, including, by the way, an EOA to EOA transaction, not only a transaction which requires a smart contract invocation. Any transaction initiation has a fixed price of 21,000 units of gas. But all of them are fixed prices. When you specify the transaction and submit it to the network, you tell the system how to convert the price in gas. The price in gas will be computed automatically. It really depends on what your transaction is doing. How to compute it into Ethereum, because the price will be charged from you in Ethereum, not in gas. So basically your transaction cost in Ethereum is gas price of transaction, which is automatically determined. It is automatically determined based on what you are doing. As I said, all those operations have a fixed gas cost, gas price of transaction, multiplied by the exchange rate, by the price of gas. Ethereum price of gas. And this Ethereum price of gas is what you specify by yourself in the transaction, by the central. In particular, you can make it as low as you wish. You may, for example, make the Ethereum price of gas even zero. But what happens? This plays the role, the whole transaction cost actually, plays the role of same transaction fees as we have seen for Bitcoin network. The miners would include your transactions into the upcoming block and try to hack this block, prioritizing them based on the total cost of the transaction. So if you specify your price at zero, then there are very, very, very low chances that your transaction would be executed at all, although it may eventually be. And it is in your best interest to provide competitive price of gas, which you can see by observing the current recent transactions over the Ethereum network, examining them through your node software, provide a reasonably competitive price in order to get your transaction executed timely. So when the transaction is eventually included into the block and the block is hashed, then the transaction cost, total transaction cost, is assigned to the miners. And even if the transaction was aborted, having run out of gas, then obviously the miners are not at fault in this case. They were really executing the nodes were executing your smart contract. The smart contract simply didn't have enough resources to run. Therefore, in this case, although the computation results in nothing to you, and it did not update the state, so obviously it didn't achieve your objective, whatever it was, but the gas is subtracted from you, the Ethereum value is subtracted from you and assigned to the corresponding miner. So that's how, in general, it works. When a smart contract is executed within the Ethereum virtual machine, you get certain objects in the context, which you can refer to and use in your computations. So what are typically these objects? One of them is called message. We have already seen it last time when we introduced. So this is smart contract execution context. Several objects. We have seen the message. In particular, the message contains information about the sender. That's important because if the transaction is, for example, a very simple monetary transaction as we have seen, then the money are to be sent to that sender, so we know to whom. Gas data could be possibly associated with a message, but this makes sense obviously only in case if the destination is a smart contract. In that case, this data are placed in the storage, persistent storage of the corresponding smart contract account. If it is a monetary transaction only, then it has a value in way. And we have seen last time that the way value can be destined to both actually EOA and smart contracts account, whereas data makes sense for smart contract accounts only. If the data are sent to EOA, then they are simply discarded. So these are properties of the message object, which you can refer to programmatically from within your, for example, Solidity smart contract. That's the most important one. What else? There is an object which is called transaction itself, and transaction itself has this value which we discussed. It has a gas price field, which is the most important one. Um, Normally, from within your smart contract, you wouldn't need to access this gas price because it is accessed automatically by the mining software when prioritizing the transactions, but you can if you wish. There is another thing which is called the origin of the transaction. There is a difference between the sender and the origin. The sender is the address or account address in the Ethereum sense, from which this current message originated. Whereas the origin is a global origin, transitive one, which means that if the original EOA invoked then smart contract account 1, which invoked and so on smart contract account n, then for the nth invocation, the sender would be smart contract account n minus 1. That's going to be the sender, where the origin will be this EOA. The problem is that somehow, due to implementation problems, although the sender is always directly known, the origin may be known imprecisely. So this is an unsafe value, which is not recommended for use. And yet another object which is available to your smart contract is the block object. Obviously, there is an application binary interface which allows your smart contract to make calls into the virtual machine and get access to all those objects. So, for example, an important thing in the block is the gas limit in the whole block. Although there is a value of gas provided in each particular message or transaction, there is a gas limit set for the whole block. Why? Because suppose that someone really has a lot of gas and is sending a huge transaction across the whole network. This is undesirable. It would mean that for whatever reason, one who amassed a significant amount of gas could stop processing further blocks by just engaging the whole network into a very, very, very costly transaction. Yes, of course, he pays for that. It is not free. He pays for this with gas, which is subsequently converted into his Ethereum and extracted from his Ethereum account, subtracted from his Ethereum account. And yet, it can jeopardize operation of the whole network. That's why the total amount of gas which can be spent across the whole block is limited. And if you include transactions into a block, and there is a transaction 1, 2, 3, and so on, the amount of gas within these transactions cumulatively must be less than or equal to the gas limit for the whole block. And there is a standard gas limit which ensures smooth operation of the whole network. There are some other per block values. So, for example, the difficulty, which is the threshold for hashing, but again, it is of value more for uh, the miners rather than for the smart contract. So, although this block information is available, block number obviously is one of the values. Timestamp is yet another one. But I would say that typically, apart from the message object, there is typically very little you need to access while executing your smart contract. Okay, so we are, I think, done. We have mostly covered everything we wanted to cover. On Monday, we'll have a pair of other lectures on Hyperledger, and then we are done for the whole course. And shortly afterwards, we'll have a final exam. If no questions, let us conclude for today. All right?
Yes, sure.
Thank you. Okay, great,
Thank
thanks.
you.
Bye.
Bye.